Lecture 1.8, Generalized one-port elements. We can categorize the behavior of one-port elements: electronic, mechanical, translational, and rotational, considered thus far. In the following sections, we consider two types of energy storage elements, one type of dissipative element, and two source elements. So in the last lecture, we generalized the variables, right? And in this lecture, we're going to generalize the elements, for what that's worth. A-type energy storage elements are first. So an element that stores energy as a function of its across variable is called an A-type energy storage element. Sometimes we call it a generalized capacitor because a capacitor is an A-type energy storage element. So this is the sort of the first one that we're going to take as being like, okay, a capacitor is like a this, is like a that. Okay, so that's what we're doing. So for generalized through variable f, across variable v, integrated through variable h, and integrated across variable x, should be a script x. The ideal linear constitutive equation is that h is proportional to v with constant of proportionality c, which is called the generalized capacitance. Differentiating this equation with respect to time, the elemental equation is, so if you take the time derivative of h, remember, is the integrated through variable. So if you take the derivative of the integrated through variable, what do you guys think you're going to get? The through variable, f, is equal to c dv dt. And we usually like to rewrite that with the time derivative on the left-hand side for no reason that you know of yet, but we'll talk about that later, why we do this. So that is our elemental equation for an A-type energy storage element. A-type energy storage elements considered thus far are capacitors, translational masses, and rotational moments of inertia. So if you think about like what the elemental equation looks here, if you were to plug your variables for translational mechanical systems into this, it would be, so v is just little v, right, the velocity. So dv dt equals, and we have something times the through variable for translational mechanical systems, which is the force, right, F. So mech translational, you would have dv dt equals something times the force. We know the force is equal to the mass times the acceleration, right? Newton's second law, so that means this has to be 1 over m. Force is equal to mass times acceleration. So since this works for a mechanical translational mass, masses are A-type energy storage elements. Okay? And then the same with rotational moments of inertia. You have the torque and angular velocity equation. Okay. T-type energy storage elements. An element that stores energy as a function of its through variable is called a T-type energy storage element. Sometimes we call it a generalized inductor because an inductor is a T-type energy storage element. The ideal linear constitutive equation is that the integrated across variable x is proportional to the through variable f with constant of proportionality L, called the generalized inductance. If we differentiate, as usual, with respect to time. We get, so dx dt, if you take the time derivative of the integrated across variable, you get back the across variable. So v, that's a bad v, v equals L is a constant, f, so df dt, and if we rearrange as usual, we get df dt equals 1 over L v, and this looks a lot like our electronic inductor, right? Obviously. So we've got, for the inductor, this would be di L dt equals 1 over L VL, right? That's our elemental equation for an inductor. Elemental equation for a spring, you may or may not remember, is df dt equals, so it comes from Hooke's law, right? F equals kx. Take the time derivative of that, we get df dt equals, k is a constant, and then dx dt is just v. So that would be the elemental equation for a spring. So T-type energy storage elements considered thus far are inductors, translational springs, and rotational springs. As with generalized variables, the analogs among the elements are more important than are the generalized T energy storage element. So a big takeaway from this section is that inductors are like springs are like rotational springs, right? The big takeaway from the A-type was that capacitors are like masses, are like moments of inertia. Okay? So we're starting to concretize our analogies here. And now we're to D-type, energy dissipative elements. An element that dissipates energy from the system has an algebraic relationship between its through variable and its across variable, called a D-type. These are called a D-type energy storage, energy dissipative element, I should say. Sometimes we call it a generalized resistor because a resistor is a D-type energy dissipative element. The ideal linear constitutive and elemental equation is V equals RF for some constant of proportionality, R called a generalized resistance. So this obviously looks a lot like our electronic V equals Ri, right? But then also we have the translational dampers and rotational dampers that behave in the same way. As with generalized variables, the analogs among the elements are more important than the generalized D-type dissipative element. Okay. So now we know that resistors are like translational dampers, are like rotational dampers, right? So that's, again, the analogy that we're making. One more note here. So we've got for the case of a mechanical translational system, we have V equals something times F, right? And we have we've used this B constant before, right? The damping coefficient. And this is inversely, so if you were to write R then for a mechanical system, R is just 1 over B, okay? And I think I have I think it might be in the next chapter. I've got a table that's got like a summary of all this stuff. So yeah, maybe the next chapter. So R for a damper is that. L for a spring, you can look at this equation and say, oh, well, L for a spring must be 1 over K then, which is the case. So, yeah, and then like for up here, we said that this was the mechanical translational version, which means that C for a mechanical translational system is just the mass. So these analogies are the important thing, though, that we're getting that they are, this is an A type, this is a T type, this categorization, this is a D type. And then finally we have sources. So an ideal, so I'm going to read this sentence twice. This is actually most of this lecture is exactly the same as those other ones that we did, but generalized, okay? So this is another parallel lecture. So I'll read it first time through this next sentence with through variable in there, but then I'm going to switch it in a second and read it again. So an ideal through variable source is an element that provides arbitrary energy to a system via an independent of the system through variable. I think this sentence is getting familiar to us. I'll reread it in terms of electronic systems. An ideal current source is an element that provides arbitrary energy to a system via an independent of the system current. Okay? So you do the same thing with force. You do the same thing with torque. The corresponding across variable depends on the system. So this element word that's in there is a typo. Currents, force, and torque sources are the through variable sources considered thus far. An ideal across variable source is an element that provides arbitrary energy to a system via an independent across variable. And so I'm going to reread it with voltage this time. An ideal voltage source is an element that provides arbitrary energy to a system via an independent voltage. Okay? So that's, we've been sort of drawing this analogy, and that's what we're doing here one more time. The corresponding through variable, through the element, depends on the system. Voltage, translational velocity, and angular velocity are the across variable sources considered thus far. Yeah. So, any questions on these generalizations? All right.